Hi again, let's continue, and our next speaker is Maciej Nowak. Now, Maciej started his adventure in professional software development over 10 years ago with .NET and a web browser. 6 years ago, he changed his career and currently works on flight software for satellites. Recently, Maciej has been part of the PWSat-2 operations team. PWSat-2 is a satellite built by a group of students at Warsaw University of Technology. In his spare time, he likes to watch Star Trek while playing with the cables connected to the microcontroller. Maciej, welcome to Code Dive.
Okay. Hello everyone. During this talk, I'm going to show you how we are using QEmu as a tool to aid us with development of flight software for Cortex-M embedded target. To give you a bit of context of background where I work for a company called KP Labs. It's a startup from Poland, from Gliwice, working in space industry. I'm part of the team that is responsible for developing flight software for embedded components. And most of developers in our team have previous experience in working with PWSat-2 flight software. We are working on software for onboard computer, and we're also part of the operations teams for the whole mission. Right now in KP Labs we are working on Oryx. It's an SDK for developing software for small onboard computers, targeting mostly bare metal devices. And beside Oryx we are working on two quite interesting projects. They are Intuition One, which is biggest project of our company. It's building our own hyperspectral Earth observation satellite. It will be launched at the end of next year, and Oryx is used there to build flight software for onboard computer that will govern whole mission. And also we are working on Antelope, which is an onboard computer for small satellites that can be programmed with Oryx as a base tool for developing software by end user. And Antelope will also have some machine learning capabilities with predictive maintenance. When we started working on Oryx a few years ago, we gave ourselves a bit of challenge how we can approach to our day-to-day development. So we wanted to know how close can we get to running our software on daily basis by every developer. How close can we get to running our software on target hardware when we don't have access to that hardware? Because problem with space components and with specialized electronics in general is that lead times are very long. Right now the problem is even worse due to chip shortage, but even few years back it was a pretty long time before we get first engineering model of our OBC for Intuition One. It was more than a year from start of the project to receiving first hardware model. And during that time we had to find some way how to work with our software to test it, but the only things we could use from hardware components were some development boards, but they were not really available or matching our target hardware. So we wanted to find some other way. Why not just work on desktop machines and compile everything there and hope for and finally compile it for ARM machine and hope it works? Well, we wanted to use single toolchain for all our development. So if there is some issue with compiler, like linker playing with us and removing needed symbols, we wanted to find that kind of issues early in the project, not in the late phases when fixing them could be a problem. We wanted to maintain the same memory constraints. So flash area that is read-only and has limited space, RAM memory that is limited, stack that can overflow other important parts of memory, or no heap, stuff like that. We wanted to stick to the same real-time operating system. We are using FreeRTOS for our projects, and we wanted to use this operating system for our multitasking capabilities, use its synchronization primitives, so we could catch all overflows or all deadlocks, problems with built-in functionalities. Also, we wanted to stick to the same interrupt model as in target hardware. So, for example, in RTOS, there are functions that can't be called from interrupts, but it's quite easy to, by mistake, call a non-interrupt save function from interrupt, and that usually leads to smaller or bigger disasters. So we wanted to prevent these kind of issues from happening. So how can we run bare metal ARM Cortex-M executable on our desktop machine? Well, we can run it directly, so we need some form of emulation. Luckily for us, the open source emulator, QEmu, has support for Cortex-M's machines, and it's customizable enough so we could use it for our needs. The first problem we hit is that Cortex-M support in QEmu is a bit limited. The only machines that are supported are a few off-the-shelf boards that are not matching our target hardware. Even our MCU is not modeled in QEmu in the way you could use it. So maybe we could write our own machine that will model our target hardware. But even if we are using exactly the same Cortex-M that is modeled inside QEmu, there is a problem with peripherals. Because in supported Cortex-Ms, and most of the machines that are in QEmu right now, the peripheral support is limited. Not every peripheral from every MCU is implemented, and even if it's implemented, there is no guarantee that will work exactly like the hardware counterpart. Of course, it is possible to write peripherals that will exactly match peripheral from real hardware, but it will require reverse engineering silicon and building code that is feature compatible and also bug compatible, so we could be sure that it works correctly. And without knowledge of how the peripheral is implemented in hardware, doing it in software is very, very hard. So while it's doable, it's not a very feasible solution. So we need to find some other way. How can we use QEmu and its emulation capabilities to work with our project? So we took a few steps back and looked how we are using peripherals in code. The code on the slide shows you very generic, a bit simplified code that handles different peripherals. This template works for most of the peripherals, and there are a few important things that we could use to model our solution. So the most important part of this code are two methods. There is doWork method and interrupt handler. The doWork method is called from some task. It receives two buffers, one with input data, let's say it's data that will be sent to some I2C device, and there is output buffer that will receive data that are sent back from this device. And inside the doWork method, we are preparing transfer. So this requires talking to some peripheral, setting up some flags, maybe setting up DMA transfer. At the end, we are sending input buffer into this peripheral. Then we are waiting on semaphore for peripheral to signal us that transfer was finished. After transfer is finished, we are reading back the response into output buffer. This semaphore that signals the transfer finish is unlocked from interrupt handler, and interrupt handler is is invoked by peripheral after finished transfer. So if we could provide some way to build very generic peripheral inside QEmu that will give us similar capability, but instead of talking over I2C device, it will talk to some other program running side by side with QEmu, we could implement different peripherals and model behavior of different buses in some, let's say, Python in some easy way, and provide a way for program running on emulated CPU to communicate with this program and use these simulated buses. Currently, QEmu supports two ways of for program running on emulated CPU to call something that is running on host machine. The first one is semihosting, and the other one is by using devices. Semihosting is part of ARM specification. It's a mechanism very similar to system calls known from big operating systems like Linux, Windows, but it's tailored to work on smaller devices like Cortex-Ms. It is using breakpoint instruction to interact with QEmu or with any debugger like JLink or OpenOCD. And when this breakpoint instruction is executed by CPU, in case of QEmu, there's some special callback that is invoked. The state of CPU is inspected, and specified operation is invoked. These operations are used by library called RDII mon. It's part of newlib for ARM targets. That library implements I/O operations for target using semihosting calls. For example, we can use print functions to output something to standard output. We can also access files on host machine, which is useful because we can gather code coverage, for example, very easily, just by linking with gcov, or we can output unit test results. So very nice stuff. The downside is that semihosting implementation is very tightly integrated into QEmu. If you look through source code of QEmu, you will find single file with quite long switch, with cases for different operations, and each case handles inline each operation. There's really no mechanism to plug in our own system calls, our own operations. So we would have to modify the file to add our own operations. So you can imagine that maintaining it will be a nightmare. Also, if ARM will decide in a few years that, yeah, we need to add a few more operations to semihosting, probably there will be some conflicts with operation codes. So not really a nice thing for extensibility and for custom operations. Also, semihosting is specific to ARM platforms. It was adapted recently in QEmu to support RISC-V, but if I'm correct, it is not part of the official specification. So this approach will work only for ARM machines, not for other targets that we might be working with. The other way to work with, to provide some communication with host machine is by using devices. QEmu is built around devices. It has a pretty extensive infrastructure for them. Most important, it's adding things to QEmu. It's not changing things already in QEmu, so it's really nice for extensibility and maintaining in long term. Devices can provide memory mapped I/O, so we can define memory region at specified base address. where writes and reads are handled by callback specified by us. So program running on emulated CPU writes some value to memory address. This memory is mapped to our device, and some callback registered with our device is invoked every time CPU writes something to that memory address. We can handle that write as we see fit. Also for reads, we can return the value that will be returned to CPU. This flow is very similar to how we are working with peripherals on real hardware. Also, most of the devices are using microcontrollers are using memory mapped I/O for peripherals. So the operation is very similar and matches what we see on hardware. Also, devices are architecture independent. There are some exceptions because working with interrupts is a bit of platform specific. But in general, memory mapped I/O works for every architecture. So if we write our device once, we can reuse it on different platforms. We started with prototype implementation of Semihosting, but quickly switched to using devices, and that's the way we are working with QEmu right now. So once we implement some sort of device plugged into QEmu, we need to provide some way of the device to communicate with some process running along with QEmu, so we do not have to implement every bus and simulation of every device inside QEmu, because that will be not very easy to do. We wanted to move it to some other process. Of course, we could use bare TCP sockets for communication, but we wanted something more like message-based communication. So we decided to use a library called Nanomessage, which provides message-based communication with some communication patterns like request-reply or push-pull over TCP sockets or many different transport protocols. And the only thing we need to do is to push messages through it. Nanomessage is similar in usage to ZeroMQ. Actually, we started with ZeroMQ, but hit some issues with event loop integration inside QEmu. So we had to switch to less popular Nanomessage. But the idea behind that library is the same. So putting everything together, we have created something called external device interface, in short EDI. Each EDI provides us with single Nanomessage socket from one side, and on the other side it's mapping into emulated CPU address space. So we have program running inside QEmu on emulated CPU, it's executing instructions, and there are one or more EDI devices, each providing a single socket. Program can talk to these devices by writing and reading from memory. Operations invoked on this device are translated into Nanomessage operations. Messages are sent and received. On the other side of the socket, they are handled by a test host application that can be written in any technology. We are using Python for that purpose. And there is some code handling each socket. And one socket is, for example, for handling I2C devices. So there is a deconic of I2C transaction, dispatching into some device simulator. Simulator responds with data, performs some operation, and responds information back to QEmu. Similarly, we can work with SPI, UART, we can have dedicated logsync, many different peripherals. We don't have in QEmu as a built-in and ready peripheral, but we are using generic EDI to escape QEmu and emulate these peripherals in some other application. From the code point of view, EDI usage is just few operation. This is the same template of peripheral driver I shown you before. but this time it is adapted to use EDI. This time the initialize method is a bit more complicated because we have to set up the EDI socket. We are starting by setting connection type. For most of the peripherals, request reply pattern works best. Then we are connecting to specified URL. We are using mostly inter-process communication with named pipes because we can easily customize the name of the pipe to avoid conflicts on CA builds. After connecting, we are wiring EDI to interrupt. So every time EDI1 receives a message, interrupt number 12 inside CPU will be raised and our interrupt handler will be invoked. Inside the work method, there are very simple operations for sending message over EDI socket using write command. And whole buffer is just sent to socket. Then we are similar to a hardware driver. We are waiting for incoming message or to transfer to finish, and then we are reading message from the incoming messages queue. On the test cost side in Python, we are using pure Nanomessage library to create socket, bind it to the same address as used in QEmu, and in background thread we have loop that handles all incoming messages by receiving each message, handling it accordingly to the protocol and peripherals. So, for example, dispatching to I2C the device simulator, some response is generated and sent back into QEmu, where it will unlock the semaphore and do work method and resume, and the program can continue. So this pattern works for I2C, SPI, UARTs, a lot of different peripherals. Because EDI wraps Nanomessage socket, it exposes most of the operation from socket to emulated CPU in form of several commands. So you have connection management, things like setting connection type, connecting, binding, or disconnecting. Disconnecting is useful for restarting the CPU, but it's not really required, and we are not using it very often. We have message-related operations like writing and reading messages from input and output queues. We also support gutter-scatter operations, so you can build single message from several buffers in CPU address space. This is particularly useful for buses like I2C, when you have to add some additional information to each request, like device address. So by providing gather operation, we don't have to copy all input buffer to some temporary buffer just to prepend few bytes. Or on the other side, combine several messages into a single operation. There are also a few more informational operations like querying the number of messages waiting in queue or size of the message at the head of queue. Memory mapped I/O exposed to CPU is just 5 registers. The command register is used to trigger specific operations. So by writing command code into it, you are triggering callback in QEmu. Pointer and size registers are used to describe buffer associated with executed command when it's required. Some operation does not require any buffer. Interrupt register is used to wire EDI with interrupt number that will be raised after receiving message. And ID register is just constant value that we can use to verify that QEmu is configured correctly. For gutter-scatter operation, there is helper structure, EDI message part, and we are just providing array of these structs to describe different part of messages. Inside QEmu, things are getting a bit more complicated. So typical flow of message is that program writes to EDI registers to trigger different operations. After write operation is triggered, the message is read from CPU address space and put into outgoing message queue. Nanomessage is integrated into a QEmu event loop to avoid any threading issues. So when Nanomessage notifies us that it is ready the socket is ready to send next message, we are getting message from queue and sending it using Nanomessage. And when message is received, we are also notified. The message is received from socket, put into incoming message queue. If configured, interrupt is raised in the CPU, and CPU can access the incoming message queue by accessing EDI registers. What is important is that CPU is not waiting for a message to be sent. It's done asynchronously. The CPU is suspended only for the time that is required to copy buffer from CPU address space and put it into outgoing queue. We had to make some changes to QEmu. We started with creating virt Cortex-M machine. It's a very simple machine. It's not modeled after any off-the-shelf board. It's just a simple CPU, and you can configure which Cortex-M CPU is used, ranging from Cortex-M0 to M33, and you can use any of CPU supported by QEmu. There are no peripherals by default. There is only a memory, both for flash and for data storage, and you can configure these sizes. Also, you can configure number of interrupts, so you can model something close that is close to the hardware, or a more generic machine, for example, with lots of flash and lots of RAM to run unit tests. This is also useful. If you want to use EDI, you need to instruct QEmu to add KP EDI device, and single device provides you with single socket. Then you can map at a specified memory address. If you want to add many EDI devices at once, it's useful to use KP EDI group device, which creates just several devices one after another in memory. So very simple command line for running something under QEmu is on the slide. So we are using virt Cortex-M machine with 2 megabytes of flash. We enabled semi-hosting, so you can use primitive debugging if something goes wrong. We are running up-elf image, and we are adding 20 EDI devices at their default base address. Right now we have support for EDI for 4 different architectures. This is mostly caused by the need to work with interrupt controller. So that's why the EDI is not very generic. But right now we can run it on Cortex-M, and that's the solution we are using in our projects right now. We have support for Cortex-R. We also had to create virt Cortex-R machine. It is using generic interrupt controller v1 from ARM. It's working, but not in production use right now. We have support for Atmegas, so 8-bit machines from Atmel, for example, Arduino, and their EDI works with any machine already supported by QEmu, and this is this platform we are using in our projects. And recently, like a few weeks ago, we added support for Leon 3. It's a Spark V8 architecture used in space mission. It's a software from Geissler, but there is already a support for it for QEmu, and we just added QEmu for it, just added EDI for it. So right now we have capability to run our Cortex-M application in QEmu, communicate with some test host application, emulate different peripherals, different devices. But the real hardware does not provide us with EDI peripherals. That would be interesting, to be honest, to have Nanomessage built into silicon. So we need some way to switch our application from QEmu to hardware very easily. And to do so, we are applied the most important law in computer science that tells us that all problems can be solved by adding another level of indirection, unless we have problem with too many levels of indirections. So let's start with typical monolithic application where we have single executable that is tied into specific hardware platform or QEmu platform that links several static libraries. These libraries provide different capabilities like driver for communication system, driver for power controller, some scheduler, communication stacks, stuff like that. And main application is responsible for building a composition route, wiring different things together, initializing hardware, connecting higher level drivers to low level drivers, and running RTOS, setting up tasks, building everything together so we can achieve our desired functionality. So what we do to switch between QEmu and hardware easily is that we convert main application to static library and remove all target-specific functionality from it, and moving that platform-specific things into runners. We can have several runners. They are just executables. In most of our projects, we have one runner for QEmu platform, so it's using EDI for all communication. And we also have a runner for a hardware platform that uses hardware-specific drivers. In that way, the main application and all libraries are independent from the platform, and the code can be shared and compiled only once. And just by linking to a specific executable, we are tying it to a specific platform. From the code point of view, this is a bit simplified solution, but shows the idea. The main application defines interface that has to be implemented by different runners. So in this case, it's a pure abstract class which provides us with accessor methods to I2C driver and can driver. There is also a single global function that provides us with reference to implementation of the peripherals class. For QEmu, we have QEmu peripherals implementation, which is using EDA-based drivers for I2C and CAN. And these references to these drivers are returned by implementation of methods from a previous slide. And this runner provides us with main functions, so the entry point to the application. We can use command line arguments. This is a nice thing provided by Semihosting. We use these command line arguments to pass values that are passed by bootloader on hardware, but here we can use just command line arguments. In particular, we are customizing our URLs for EDI, so we can have concurrent integration test runs on CA machine without conflicts. Inside main function, QEmu peripherals are initialized, so all hard or QEmu specific things are started here. And after that, we are jumping to entry point provided by main application. Similarly for hardware, we have hardware peripherals class using MCU specific drivers. Also there is main function, this time with no command line arguments because there is no command line for hardware targets. If there are some arguments passed from bootloader, we need some target specific way to access these arguments. But similarly to QEmu, we are initializing the hardware specific stuff and also jumping to main application entry point. So we are using QEmu and EDI and the structure of application I showed you on the few last slides by whole team for over 2 years. Whole Oryx was developed is developed using this software. we have a huge suite of integration tests that can be switched between running on QEmu or on hardware just by changing command line argument in PyTest invocation. And it's really nice because we can share our tests between these platforms and make sure that they work on different platforms. Our Jenkins is running both the suites on every build, and you can see that hardware is a bit slower than QEmu, like twice slower than QEmu. And what is most important for us, that most of the problems we had and bugs we introduced in our code base were found on QEmu. So stuff like stack overflows, deadlocks, some running overwriting some important memory parts. We found that on QEmu without touching hardware. Most of the team is not using hardware on daily basis. We are basing only on QEmu, and the hardware is moving between team members as needed. After a year of development, under QEmu and very limited development board, we had a lot of code. Then we received our first engineering model from our supplier. We added few missing drivers, executed run it on hardware platform, and it worked. It was very, very nice because there were no very important bugs when we used target hardware for the first time. The whole high-level functionality was working correctly. So that was really nice. And during this year of development, we found a lot of issues with compiler, toolchain, and linker playing with us. And if we started solving this problem after a year of development, it would be pretty hard to do it very easy. What we discovered in the last few months is that porting EDI to different architectures, different machines, is very easy. We started with ARM Cortex-M only, then added support for Cortex-R. Then some projects started that were using Atmega's Spark, and porting EDI to these architectures was just a matter of implementing glue to interrupt controller. Also, when we started working on project with Leon 3, we didn't have any hardware with Leon 3, but we needed to start with something. So even run some hello world, handle interrupts, and we started with using only QEmu. And it was really nice because there were already support for Leon 3 in QEmu. And we had some problems with handling interrupts and using interrupts in Spark. But just by investigating the source code inside QEmu, how different things are connected together, by studying the source code, we understood what is happening inside CPU, and we could learn something about this architecture without digging through poorly written manuals and datasheets. But we could just investigate what's happening in the source code. If you'd like to play with QEmu, on our company's GitHub, there is a fork of QEmu. It's not up-to-date version. It's 5.1 version, so like year old. We are in process of upgrading into the upstream, but it's still pretty up-to-date version, and it has support for EDI, all these virtual machines I told you before, and few extra things. There's also a repository with headers for EDI, two headers describing the memory mapped IO API, and a bit of documentation. And on my GitHub, you'll find a demo using QEmu with EDI with Python to demonstrate how different things are connected, and also following the structure, allowing us to separate QEmu and hardware specifics from main application. So thanks for watching and listening. If you'd like to talk with me about space stuff, bare metal development, or QEmu itself, using EDI or developing things for QEmu itself, because it's quite interesting platform. There are a lot of different peripherals already built in. You can reach me via Twitter, or you can send me an email. The contact details are on the slide. So thanks again for watching, and have a good day.
All right, lovely. Thank you so much. This was Maciej Nowak. Thank you for your talk. And don't forget about our virtual escape room. Check our website right after the conference. Hack Dive is waiting.